Hello, hello, Vicky. Hello. All right, there they come. Hello, Lear. Good to see you.
Good morning. How are
Good
you?
morning. Good, thank you. Good, thank you. Awesome. That's voice. That's video. That's so many points. And that's Vicky with the animated avatar. That's points. Victoria with the avatar. That's points. Mafine. Good morning. Sonam, Caitlin, and Fabia, all with the avatars and all points.
Good afternoon, Professor.
Well, good afternoon. Who? Oh, Mohammed with the voice. Awesome. Good afternoon.
Good afternoon, Professor.
Who
Quick
is that?
question.
Melanie. Good afternoon. I love it. Oh,
Good afternoon,
oh
Professor.
my God, this is amazing. Wait, actually, who was that? Wait.
Listen,
Oh, Mafid. Oh, great. Getting to know you. That's awesome. Thank you. See, if we do this right, we can all get tons of points and never even have to talk about physics. How perfect would that be? No, I'm just kidding. No, but that's great. All right, hang on one
question,
sec.
Professor.
Oh, yes, yes. Where is
So
that?
I'm looking at the homework that's due Wednesday, right? We don't have school this Wednesday and we don't have school next Monday. So is it possible we can push that homework to the following Wednesday that we do have school? Because it's a lot.
100%. 100% yes. No, thank you for reminding me. I totally
Thank
did not realize. Yeah. And you're talking about, I mean, the answer is yes, but you're talking about homework
the
to mathematics.
mathematical, yeah,
Yes.
that
Perfect. Perfect. Yes, yes. And you can all thank Melanie privately for that. Yes, I will. In fact, oh, and good afternoon. I haven't even said good afternoon. Yes. Again, I didn't even realize we didn't have school this Wednesday, or I forgot or whatever. I'm going to I'm going to change that now. In fact, yes, yes.
thank you
Great.
so much.
No, thank you. And thank you for pointing it out. Hold on. So, in fact, I'm going to pause for a second oh, and thank you. Yes. And thank Hey, by the way, that's multiplayer. If you thank Melanie for that, you get multiplayer co-op, and so does she. I'm serious. That's how, and bear with me for a second because I'm literally going to change that right now. Of course, guys, she says, okay. And good afternoon. Sorry, I'm going to the chat. I'm going to the chat. Yes. Good morning, Gabriel. Good morning. I think it's the afternoon, but anyhow. Good morning, Gabriel. Good morning, Victoria. Hello, Anthony. Good afternoon, Vicky. Good morning, Sonam. Good morning, Fabia. Good afternoon, Amanata. Good afternoon, Caitlin. Good morning, Zoe. Good afternoon, Mafine. Good afternoon, Joel. Good afternoon, Raina. Yeah, I appreciate your appreciation, David, et cetera, et cetera. Okay, that was all the thank yous to Melody. Awesome. All right, we're going to start in a second. But let me change that right now before I forget. Bear with me for a second. And yes, that is a lot. But yes, anyway, okay, hold on. Wait, but you have, oh yeah, what are we saying? Are we from, okay, hold on. I'm not taking it back, but wait, are we saying, I mean, technically we have
So
this,
we don't have school this Wednesday, and then this next Monday we also don't have class.
right?
So and we have class that Wednesday. So is it possible the homework could be due that
Yeah,
Wednesday?
yeah, the only slight thing I want to say about that or make sure is don't we actually have class Tuesday instead of like I believe this isn't a
Oh,
big
okay.
right? So I think technically I want to make it do well. Now
If
I'll
it could be done, if it could be due, I don't care. As long as it's pushed back, I just
yeah,
need to.
it's pushed back. It's definitely pushed back. Yeah, let me just think for a second whether I'm making it Wednesday or two. Give me one second. But yes, yes. But also just to remind everybody, we do have we can push it. Wait, 12. Yeah, because we have this other thing due. Okay, okay, hold on one second. Hold on. But just to everybody, yeah, just to remind you, whatever I do with this homework, we do have class next Tuesday is a Monday schedule, which is crazy when they do that because obviously that is not true at your jobs or with your husbands and wives or your parent or like whoever you live with. It's not true when we just say whatever. So, and in effect, anyway, but we do technically have class next Tuesday, pretending it's Monday. Just reminding everybody of that. I'm reminding everybody of that. But yeah, what I do about the homework. Okay, hold on one second. Hold on. Oh, I can make it. Um, okay, no, she's right. I'll do, yeah. All right, I'm gonna do what Melanie says. I'm gonna make it Wednesday, like she says. I just have to change a couple things right now before I forget to adjust for that. So bear with me.
So we have class next week, both on Tuesday and both on Wednesday.
Correct, correct. Yes.
Okay.
Yeah. Yeah. Thank you for okay, so then this will be oh, sorry. Okay. I believe I believe this is now right. Wait, let me just look for a second. Yeah, and let me fix. So you should see it was upgrading Google Classroom by just doing the other. Okay. All right, and bear with me for one more second, then I'll explain one other thing. I mean, one other logistical thing. Um, okay. Okay, so a couple of things. We'll get back to physics. So yes, no, thank you for that correction. Again, so we do have class next Tuesday. We don't have class this Wednesday, thank you. We don't have class this coming Monday. We do have class this Tuesday, next Tuesday, and next Wednesday. That is true. The homework, so again, thanks to Melanie, just to be clear, the homework that was due this Wednesday is now due next Wednesday. The homework that was due then is pushed a week. Now, somewhere this will all, it didn't push anything else. Like it'll all work itself out, partly because it is true that we spend a long time talking about homework one, which I'll get back to in a moment. And it's true that homework two is very long. It is. Then homework three, just so you know, and somewhere in there, there's also homework 1B. I know that, but I'm just putting that aside. Like in terms of all the mathematical homework, homework three, by the time you get to it, is very short, oddly. The truth of the matter is homework three. So that's where all this time will catch up with itself. Just so you know, yes, homework two is kind of a slog. Like it takes a while. I'm glad Melanie like pointed this out. But almost like the reward for homework two is homework three, where by the time you get the concept, that's being drummed in over and over in homework 2, and that the concept that we're going to start today, then homework 3 is like one quick exercise in that concept. Like if you get the concept, homework 3 is, well, no matter what, homework 3 is one problem with a couple of parts. And if you get the concept, then the one problem goes very fast. I'm just like warning you. So it's kind of a little bit of a like a break or like a reward for like all the work that you put into homework 1 and homework 2. And then just so you know, also often homework 3, because you have to get it to get it, you have to get to that point in your understanding to find it straightforward. Then often that homework 3 is reprinted as the basis for a problem on our midterm exam. Often, like, well, of course, we'll talk about that when we get there, but just so you can plan your life, like homework 3, by the time we land there, it's like a review exercise that we kind of use as an exam problem. So I just, in other words, that's why I changed that date also, so that we could all be clear on this. Now, as far as homework 1, like, so we're going to go back to physics in a moment. But of course, I've already sort of fallen behind with some of you in homework 1. If you turned it in on time, many of you got feedback, but some of you now have gotten points without feedback. Let me tell you exactly right now what the feedback, just so that, because I don't want it lingering I don't want you lingering without any understanding of your homework 1, like for a whole nother week and a day or whatever. So if you just got back homework 1 and it doesn't seem to have any feedback on it, if you got a 31, like please like write this, like obviously if this applies to you, if you got a 31 on homework 1, what that means is you are doing everything right. You're doing all the steps. I appreciate it. I see that you're doing all the steps the way we want. Whatever you're doing, you should keep doing on all the rest of the homeworks and the exams. Okay. But that probably, so, and your answers are all correct. If you got a 31, it means your steps are correct, your answers are correct. I like didn't like give you like Hello Kitty puffy stickers, but like if you got a 31, everything is correct and good, and you should do that again in future homeworks. But somewhere in the middle of problem 8, or more likely problem 9, things fell apart for you, or you stopped, or you got a wrong answer, or you wrote things that weren't sufficiently explained. And so when we start talking about problem 9 and going over it and getting more clear on it together today in class and next class, then when you redo question 9 more thoroughly and resubmit the whole thing, then you'll get all 35 points. So 31 basically means we just need to rework problem 9 with my help from the class, and you can take your time to do that. Okay, that's if you got a 31. If you got a 29, it basically means the same thing, except that, and you're still doing the steps and doing them correctly, and most of your answers are correct. But if you got a 29, it means I'm missing step 1 from you, probably, i.e., diagram. Or maybe you even put a diagram, but you just copy or pasted it from my sheet. We don't want that. We want every document to start with original diagram. Like, of course, it can be all the information can be copied from a diagram that I present to you, but like you have to use your hand or your computer to create the diagram and fully label it. Like, I need your diagram at the beginning of every document. Then you can constantly go through the document and say see above, see above, see above. That's fine. But if you got a 29 instead of a 31, it probably means either you're missing, like I don't see any diagram at all, or you copied and paste again, or you copy pasted it. None of this is a criticism. None of this is a punishment. All of you can still get all the remaining points. But just so I want these habits to be in place for the future homeworks and the exams. Wait, last thing about that, a couple more things about that. Oh yeah, especially because like math, I mean, homework 2 is very mathematical. I don't even provide you with a diagram but that doesn't mean you're not making diagrams. You are at least one at the beginning. What diagram would you make at the beginning of the very mathy homework 2? You'd make a cosine graph, would be my recommendation. And you would fully label it. Like again, pro tip. When you make a diagram, you'll know you're done, and the diagram has done its job if every single constant or variable that you're going to end up using to solve the problem is somehow a label in your diagram. That's the point, is the diagram uses labels to define all the terms of your step 4, of your step 3 and step 4. So last thing I'm going to say, we're going to hopefully start getting to this today, but like omega, which we haven't learned yet in the class, but like omega starts becoming a issue, and that you use a lot in homework 2 and homework 3 and stuff. You're gonna have to show that you understand what omega is by making a cosine graph and somehow making a label that shows what omega refers to in that cosine graph. That's like my advice. So for homework 2. So we want to be in the habit right away with homework 1 of always having a diagram. So I'll move on. But again, I apologize if I didn't give you personal feedback. I'm trying to save a little time here. If you got a, what'd I say? If you got a 29, it's because you're missing diagrams, I believe. If you got and that you probably have to rework question 9. And if you got a 31, probably you just have to rework question 9, possibly then a question 8. If I'm wrong about this or you have any questions, obviously, again, just email me or text me or just upload the document again. Just like write me a comment in the document thing and say, I know I disagree. Like, I think you missed something here. Like, I think I deserve all the points. Like, I'll look at it again. But okay, that's that. Oh, last thing about getting homework back and stuff. Last thing is, if I ever write www, well, I hope it's clear. If I write something like DFP or GDP, like I'm talking about the 5 steps, which I'm very concerned with the 5 steps. But if I ever write www, let me back up. But yeah, if I write www, that means what is this? Why is it true? Where did it come from? It's not meant to be overly, I mean, it is kind of overly cute, but it's not meant to be sarcastic. If I write www, what I'm basically saying is the thing that you just wrote might very well be true. It might be true, and it might even be the correct thing to do. But I feel that it's coming out of left field. Like if I write www, it means we need more explanation and support for this equation that you just wrote. That might be other equations or it might be English. It might mean I need more English for this. But and so that's especially true for equations that haven't been introduced anywhere earlier in the document or in the class. Like even if they came from the web, like you got to show me, even if they're true, you got to show me why they make sense and why they're all of a sudden happening here. So that's what www means. Okay. Okay. Oh, I'm looking in the chat. A diagram. Well, every question, for each question in homework 2, always in any given document, all the things I'm always saying, like about all the steps for a diagram, for explaining that in any given fresh new document, you got to explain everything at least once. But then throughout the document, you can refer back to the beginning. So like in homework 2, I definitely want a diagram at the beginning of the first question, and I think it would be a cosine graph. But then for sure, if there's a bunch of questions that are really similar to it that would have the same diagram, you can just keep saying for diagram C above, but say something like that. I know, hopefully that answers Melanie's question. I'm not sure. And I'm gonna go.
For the first question of the homework, you just want one graph and then we can just continue from there, like saying step 1, see diagram above,
Yeah,
etc.
exactly. Exactly. Perfect. Yes. Yes. Awesome. And the summary of all of that, this is one other acronym that sometimes I use. Or if I ever write on anybody's homework or exams or anything, if I write self-sufficient document or SSD, which isn't really if I write self-sufficient document, I mean essentially the thing that like Melanie just asked, that clarified. What I mean is you always want to produce a document that the reader, that I don't need anything else other than my own understanding of physics to follow your document. Like the test is, could you give your homework to a different physics professor or a different physics person in the world, or someone at the MSRC or whatever? Could you give your work to someone else who doesn't have the original questions but does understand physics And could they follow everything you're doing? A document that stands on its own. That's what you want. And again, I'll just say, like with everything else in this class, partly, sure, it's to make things much faster and clear between you and me. It's to help me grade things and get them back to you in any reasonable amount of time. It is partly that, for sure. But it's also like the right skill for producing like articles in journals or any kind of scientific research. Like you want always to be presenting a document to your reader that doesn't assume that the reader was like in the same conversation as you were before you wrote the document. Like, right? It's like should invite the reader into a new conversation where you lay out all everything they need to have that conversation. Okay, but I think that's so. All that said, pardon me. Okay, so so how am I flowing in the middle of the building? Wait, that's hilarious, I think. So that's the view from my window. Okay, but yeah, it's fake. I mean, that is the view from the window in my office, but I'm not in my office right now. It's a fake background, but apparently it's very convincing. Also, I'm magical. Sorry, Victoria, you have a question. Yes, please. Yes.
Hi, for for homework two, do we need the five-step method? Because I know for some of the questions, they're just the derivatives. Like, how do we draw the diagram for that?
Oh, wait, right. Good question. So yes, even for homework two, let me back up for a second. For homework 1B is the one place that you don't need the five-step method, like the unthingy things sort of cute. Homework, you don't. But yes, homework two, the math methods, you do need the 5 steps. The diagram, I would recommend a cosine graph. The purpose of the diagram, some graph, like a cosine graph that would have clearly labeled axes. And I don't mean like a million points. I mean like like label like the y-intercept, the two axes, and have a clear trend, a clear cosine trend, but then label what is meant by omega in that cosine graph. So that's the diagram. But say, and we'll get to this. I mean, I will practice this with you guys but say you're taking derivatives, right? Which is something we believe we know how to do from calculus class. Step four would be you actually like taking the derivatives, like doing the computation out. But step three would be where you write the rule or the general principle or the definition of what you're using in order to take the derivative, such as, for example, and of course I will like show you this, but for example, if you think you're using the chain rule to do a derivative in step four, then step three, write the chain rule in some kind of way. Like, I don't mean like a million page thing, but like in some quick notation, write out like that the chain rule is always true. Or if, for example, you're believing that the derivative of cosine is negative sine or something, or the derivative of sine is cosine. Well, that would be a step three, right? That's a truth that you believe even before you got to this particular problem. So you would put that as step three, and then you would, or both, and then you start applying those concepts in step four, and then circle your final answer and stuff. Do you see does that? I mean, I think that's a really good question.
Yes.
Okay, great. Oh, and she just said yes. So that's more points. All right, awesome. But great question. Okay, hold on. And I hope I answered Lachman's question. Okay, wait, there's something else in the chat, and then question. Oh no, yeah. So sorry. And I think I said this last time because I don't want to confuse. Homework 1B is the one exception to all this. You don't have to do 5-step method for homework 1B, but it still would be nice to have a self-sufficient document. Like honestly, and it may be too late. I may have already put the points on this, or I may have already let you off the hook, but even homework 1B, like it would be nice if I could read it and know what question you're asking without me having to take out the original questions. But yes, you don't have to do the methods for homework 1B, if that's what we're talking about. Okay. Thank you. Oh, and that was a thank you. Awesome. So that you got points for that, closing a conversation. But okay, so are there any wait, how did Vicky just turn into okay. Wait, how do they move? I get it. Sorry. Okay. So I think I'm gonna go back to physics now. Um, yeah, I want to go back to start getting to the hard parts of homework 1A so we could start moving on So I'm going to save a little, so last time we did all this work, we did all this like energy conservation stuff to figure out question 4 and 5, right? I'm not going to redo that now. I want to move on, but I want to say what math was underlying that. That's what's on the board right here. I'm going to try to be like the 3 equations that are not circled. I want to try to summarize right now. This is not going to what I'm about to say is not a full explanation. It's not like full teaching. It's a summary. And you should use this to say to yourself, if you already know what I'm talking about and it's clear to you, then good. But we need to know these things for this class. But if it's really fuzzy to you, what I'm about to say, or it goes too fast, or you should make a note and email me or text me. Honestly, if what the top 3 equations, you may not recognize. I'm about to, in fact, I'm going to add an equation right now. Hold on one second. Okay, I'm going to quickly explain each one of them right now, but quickly, sort of as review. You should take this as a sign that we need to know these equations. And so if they're fuzzy, send me an email or a text. And if enough people do send me an email or a text, then I will actually spend class time slowing it down and explaining. But if only a few people do, then I'll like talk with them individually. Okay? Honestly, because. So the very first equation there, it says that the definition of work is the path integral of force, right? Work is the integral from one position to another of how force is acting along the path from one position to the other. And when I say path, I mean physical path. Like I mean the route or the distance, the actual journey from one place in space to another. So what I think it means to calculate work, this is what I think that, like, I mean, I know you've all had integrals in calculus and all that, but I also know it's probably still fuzzy for many of us. And I know that if you're anything like me, you sort of maybe know how to take certain integrals, but don't necessarily always know why you would use an integral or when or what it means or how to set it up. If you're like me, at this stage of the game, I knew how to take certain integrals, but I didn't really know what I was doing when I did that or what it all meant or anything. So let me try to remind you briefly now. When we say that work is the integral of force with respect to displacement, what we're really saying is you imagine yourself taking steps along some path through space, like from one place in space to another place, from one position to another position, right? And you're on some one-dimensional route from one position to the other, like a line, right? And you take one step at a time along that line. Each little step you take, we call dx. We call it dx because it's because it's like a difference from x1 to x2. It's a difference in position, so it's a little displacement, right? You take a little step, and then you ask while you take that step, how hard and in what direction is the force acting during this step? Like you're like pushing a box along this path. And at each step that you push the box, you ask yourself, how hard am I pushing this box? And at what angle am I pushing this box? Right? And then you multiply that amount of force by the amount of the step that you took. So you literally multiply some number of newtons by some number of meters. You multiply them together. So that's F dot dx with a couple more details I'm going to throw in a second. But basically, you take the force in newtons, you multiply it by the size of the step measured in meters, you throw it into your bag, into your mind, but like you throw that product into your pocket, and then you take the next step and you do that again. You ask, what's the force now? What's the size of the step now? You multiply the two together, you throw it in your bag, the bag in your mind, you take another step, and you keep doing this, and you keep accumulating all of these products until you get to the end. And now the entire sum of all of these products is what we call an integral. An integral is a sum of products always. And that big sum, that big entire collection of all these newtons times meters is what a physicist would call the work that was done throughout that path. Okay. Yeah, but let me make two modifications to that. And again, you'd like just looking. Okay. Just hopefully you're taking notes on this or writing this, or whatever you do or don't understand about this. Two modifications I have to make now. First of all, every time you took a step and you looked at the force acting, I said, like, notice the angle that the force is making. Well, yeah, notice that there's vector symbols over the F and the dx. And notice that those two vectors, so F is a vector. Force has direction and magnitude. Displacement also has direction and magnitude. We're multiplying two vectors together. We're multiplying together in a way that we call the dot product. Like there literally is a dot between those two symbols. That signifies that and this comes up in homework 2 at the end, and in theory came up in physics 203, but it depends like which professor you had. So what I'm saying is, I'm saying sort of quickly now, when you multiply two vectors together, according to a method that when you multiply two vectors together so as to produce a scalar, if you multiply two vectors together to get an answer that does not have direction, that is called a dot product. It's literally signified with a dot. In fact, I'll write this. Well, yeah, no, I don't want. And what you're literally doing, well, here, I'll write on the next page. I'm a little worried about starting on the page, but if you have two vectors, vector A and vector B. So this is in general, right? If you have two vectors, vector A and vector B, they're different sizes and they're different directions. They're separated by an angle theta. When we dot one vector with the other, what we are doing always by definition is we're getting a scalar. When we dot them, we're doing an operation that produces a scalar result. And the way that works is we take the magnitude of one vector, multiply by the magnitude of the other vector. Notice now I'm dropping the arrows. I'm just taking the size of one vector, multiplying by the size of the other vector, and then multiplying by specifically, explicitly, the cosine of the acute angle between them. Like always. It's not like sometimes, that's not an example. That's like always true. It's a triple equal sign. What am I saying? Like, why am I? So I'm saying A dotted with B always yields AB cosine theta. I mean, so for example, force dotted with displacement literally means force magnitude times displacement magnitude times the cosine of the angle between them. Why the cosine? I'll say sort of quickly, because the sine of 0 is 0. The cosine of 0 is 1. When you multiply by the cosine of an angle between, what you're looking at is how parallel the two vectors are. Like when two vectors are purely parallel, when the angle between them is 0, the cosine of 0 is 1, you'll get 100% of the product of the magnitudes of those two vectors. In other words, the dot product is a way of looking at how much two vectors are lined up on the same axis. The more they're lined up on the same axis, the more we can treat them as just two numbers on a number line and treat the multiplication thereof as the multiplication of two numbers on a number line. Like if they're purely parallel, they're pointing along the same. So in physics wise, work is the dot product of force times displacement. Because when you push a box along the floor, if you're pushing it at some angle along the floor, only the horizontal component of your push, only the cosine component of your push is lined up with the direction in which the box is traveling. Only the cosine component, the component of your push that's parallel with the displacement, only that is affecting the displacement of the box in any way. All the fact that you're pushing somewhat down is not helping the box go across the floor. So we only multiply components that are parallel to each other, and then we get a pure number in the end, a number of joules that represents the work that we're doing. And it's not joules to the east or joules to the west or anything like that. It's just joules, right? So I'm saying this a little bit quickly, but I'm saying from now on, dot product between two vectors means the scalar product of two vectors means how much one vector is parallel to the other vector. That's totally the kind of multiplication that we use when we're computing work, right? So you see that's a dot product in there between F and delta X. I'm just looking at the chat. Okay, I'm almost, so that's one modification. When I kept saying you walk along this path, and you ask what the force is doing and you multiply the two together and you throw it in your bag, I'm actually specifically saying you don't just like multiply two numbers. You do a dot product of these two vectors. You multiply one number by the other number by the cosine of the angle between them. If they're purely parallel, then it is like multiplying two numbers. If they're purely perpendicular, you'll get zero every time. Like when you push a box across the floor, gravity is always acting on the box, but it's never doing any work, because the angle between gravity and the floor is always zero. Okay, so that's one modification. That the multiplication we're doing here is a dot product always for work. The other modification is that every step you take is dx. We're not calling it delta x, we're calling it dx. What does that mean? It means it's an infinitesimal step, right? And you remember this from calculus class or whatever. Like this is always true of integrals. Integrals always mean you take an infinitesimal step along the x-axis. You ask, what's the value of the y? You take an infinitesimal step along the x-axis of some function. You look up the y-axis. You look up what's the value of the function at this point, right? So it's like you take a little bit of input step. You ask yourself, what's the output of the function at this point? You multiply the two together, right? You multiply the width of a little rectangle times the height of a rectangle, right? If you're looking on a graph, I'm saying, you multiply those two together, you get the area of that little rectangle, you throw it in your bag, then you step to the next rectangle and you do the same thing again. Again, if it's just a graph of any kind, you're multiplying input by output and getting little rectangles. If it's physics specifically, the input is your displacement along a geographical path in actual space, and the output is force, right? So you take a little step, you ask what the force is acting at that step, you multiply the two together, you throw it in your bag, and then you take the next step and you keep going. And you make all of these steps infinitesimal so that no matter how quickly the force or whatever output is changing its value, even if it's changing its value continuously throughout your travels, you're going to catch every possible value of the force. In other words, you'll get the full area under the curve as you're walking through the graph, because each one of your steps was so small that it was infinitely small, that you caught any and all variation in the f as you added it all up, right? So the integral is always the continuous sum of products, always. The products are always a little step, an infinitesimal step along the input of the function and the times the output of the function at that step. I mean, okay, that's a mouthful. That's like half of your calculus class. But I'm saying work. Like basically what I'm really saying, I'm going to move on. But I'm basically saying, unless there's something in the chat, okay, I'm basically saying this. If you're a little fuzzy on the concept of work, but you feel like you really understand calculus and integrals, then I'm telling you, work, the concept of physics work, is the most fundamental, central integral in physics. Whatever you understand about integrals, apply it to the concept of force. And that's what work is. Okay, work is technically the path integral of force. Why am I calling it path integral? Because it's the integral that you get when you literally, when space is the actual independent variable, like as opposed to time or something else. Okay, and conversely, if you never were that comfortable with integrals, which is many of you, I mean, let's be honest, many of us. I mean, I was not comfortable with integrals for the first like 5 times I took calculus classes. Like, really, I did them, but I didn't know what they were. So I'm saying the reverse. If you sort of think you understand what work is force times displacement over the long haul, then use that to help you picture what we mean by integrals from now on. An integral is always a continuous sum of products, and the product is always input times output, like always. And it's continuous in the sense that the input steps you take are infinitely small. Okay. Okay. I mean, I'm looking at the chat. Great, great, great. Is work a sum of the changing force along? Yes, exactly what I'm saying. Aminata. Yes, that is exactly what I'm saying. So good. So yes. I mean, I literally can't add anything to that. Right. That's awesome. Yes. Put that, submit for points. Okay. So yes. So work is always now that, like the continuous sum of force displacement products for some path. Now that's a triple equal sign. That's what work always it means from now on. Now, why do we care? Well, equation 2, that's like off written to the right. Why we care is that what work does, double equal sign, what work does is it transfers kinetic energy. Right, hold on, I'm just changing the screen for a second. One second. Where'd it go? Hold on. How do I, wait, sorry. Oh, yeah. Yeah, okay. What work does is it transfers kinetic energy. That is to say, if I push you through some path or I pull you through some path, if I push you in the same direction that you're going, if I do positive work on you, whoever you are, you're a box, or you're a mass at the end of a spring, whatever. If I push you through some path, then the consequence of that is I give you kinetic energy, 1 FMV squared, right? And if I do negative work on you, I take away kinetic energy, 1 FMV squared. Oh, there's something in the chat. Hold on. Yes, number 3. Okay, so I'm about to get to number 3. I mean, it's a closed integral. Okay, good question, Lachman. I guess I'm about to get to that right now. So just in summary, so far what we have is work. Work is defined to be a line integral, a path integral along an integral of a bunch of dot products along a path. The purpose of work in physics is that what it equals is the change in kinetic energy of whatever you were doing work on. So that's equations 1 and 2. Now, equations 3, the one that Lachman's asking about. Now, this is this is a new step that I don't think anybody has heard before in a physics class, and you may or may not have seen in a math class. I'm now going in a funny order. Now I'm doing an integral in step 3. I'm sorry, in equation 3. I'm presenting an integral that doesn't have x1 and x2, like doesn't seem to have boundaries. It doesn't seem to be a definite integral, but it has a circle around it in the middle. What I want you to write in your notes, again, I know this is a lot, but whenever you see an integral if you see one integral with a circle on it, that's called a closed path integral. or you could say a closed line integral. These are both line integrals, but I like to say path. But yeah, so I mean, the answer to Lachman is yes, but the first equation is just a regular everyday path integral. It's a definite integral from one location to another location on a path. The second integral is what's called. Oh, good question. Right now, I'm not really talking about any question yet. Good question. I mean, I'm backing up and giving facts that I think were really used for question 4 and 5 on homework 1, but I'm just sort of teaching right now. I'm just sort of like reviewing or expanding on concepts right now about work and energy. So this is all, I'm backtracking slightly and talk about concepts that we use to solve question 4 and 5 and 6, I guess, on homework 1. But you're right. I mean, fair question, Lear. I'm not okay. Sorry. Yeah. So I'm like sort of off page right now, and I'll get back on page as soon as I can. My goal is to build all this and to get to question 9. That's a goal. But I'm just like making sure we know these things before I move on. So, if ever I have an integral with a circle on it like that, that's called a closed path. In fact, okay, let me write. So again, I'm like doing just general math and physics notation here that we need. So if in general, if you have a function y equals f of x, then from now on, if I say something like this, um, let me make this small. I am writing that, but I'm just gonna write it small. Okay, in general, in math and physics, a very important kind of integral that many of you may not have seen before is what's called a closed path integral. We could see it's closed if you put a little like a circle on the integral sign. And so what the circle means is it's a round trip. It's not literally round because this is all in one dimension that we're talking about, like one dimension along an x-axis or one dimension of space. But if it's got that circle, it means you go from somewhere to somewhere and then you come back to the original somewhere. Okay, like literally it's like x1 to x2 plus the integral from x2 to x1. Yeah, from x2 to x1, whatever x1 and x2 are. So it's still a definite integral, but it's a definite integral where the original boundary is the same as the final boundary. Now, that's just a piece of notation. That's called a closed path integral. What I'm now saying as a physicist, and again, yes, I'm like off page right now. I'm just like teaching something. That's a closed path integral. Well, okay. As long as you can picture what I mean by a round trip in 1D, then that's what I'm talking about. Now, why do I care? Because in physics, if the closed path integral of some force always yields 0, then we call that force a conservative force. This is the stuff that I was like assuming or using to solve questions 4 and 5 last week so that we got answers. We did all this computation, we got answers, but like in the back, remember the original thing I said in English to do 4 and 5 was if all the forces doing work on a system are conservative, then blah, 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 blah. Right? So now I'm like expanding on exactly what we mean by conservative in physics. It's like a big concept, particularly for this course. So I'm saying okay, what I'm saying from now on, what is a conservative force? The mathematical definition of a conservative force is one that does zero work around a closed path. That is some forces, that is not other forces. I'm going to say this quick. I would suggest you put this in your notes. I'm not. Yes, I am. Okay. Just very quick. So examples of conservative forces are the big ones for this class, like the spring force, F equals negative kx, the gravitational force, F equals mg or F equals gmm over r squared, the electrostatic force that we're going to get to big time in this class, like kqq over r squared. These forces are all conservative. They, like, just looking at the time. Let me just think for a second. All right. Yes. So follow the, and again, stop me if, and I will get back on page soon, but you might think from this. So I'm saying a conservative force is one that does zero work around a closed path. You might think that that should always be true of all forces, but it isn't. Think about friction or the normal force, like either one of these contact forces. If you're pushing a box along the ground, right? While you push the block along the ground and you look at the work that friction is doing on it, while you're pushing the box to the north, friction is pointing to the south, right? It's going against the motion of the box. So the box is being displaced to the north. Friction is acting to the south. So one of those is positive and one is negative. A positive times a negative equals a negative, right? So while you're pushing the box along the ground, friction is doing negative work. It's taking kinetic energy away from the box. Now, everybody knew that. I don't think anybody like questions that, right? But now check this out. Check it, check it. You push the box all the way out here, say 5 meters. Now you turn the box around, you start coming back to where you started, which you could totally do. So what is friction now going to do? Well, now the box is coming to the south. The displacement is now south, but of course, friction is going to flip the direction of itself, of its force, So now friction's going to point to the north, right? In other words, as you would expect, friction's going to flip because the direction of the box just flipped, the velocity just flipped. So friction's going to continue to do negative work as you bring the box back here. And you would expect that too. Friction is always sort of fighting against the motion of an object. So on the way out, friction does negative work. On the way back, friction does more negative work. So by the end of the whole round trip, friction has just taken away a lot of 1/2 mv squared from the box, right? It took some away on the way out. It takes even more away on the way back. And you could tell that because if you did this box along the rug, you generate a lot of heat on the way out, right? And then you generate even more heat on the way back. So friction is always doing negative. If it did negative W on the way out, it does negative 2W for the whole thing. That's what so friction is not conservative. What it takes away, it does not give back. Same thing with the normal force, but that's positive instead of negative. Gravity, on the other hand, and springs, on the other hand, let's just look at gravity for a second. Oh, okay, and I will move on in a second. I'm watching the clock. Gravity, you throw something up. On its way up, it's displacing up. Gravity is pulling down. So gravity is taking energy away from it on the way up. It's taking away kinetic energy, it's doing negative work, taking away kinetic energy. The thing's getting slower and slower on the way up. It reaches a peak height, then it starts falling down. Now, when it's falling down, it's displacing down, right? But gravity's still pointing down. Gravity doesn't do what friction does. It doesn't flip its direction. It's always pulling toward the equilibrium position known as ground. So on the way up, if you throw an object up for some round trip, goes up because it kind of like if you took Physics 203 at John Jay, like kind of like Lab 5 at Physics 203, when you send something up an inclined plane and then it comes back down, right? On the way up, gravity's doing negative work, slowing the thing down. On the way back down, gravity's doing positive work, adding kinetic energy, speeding the thing up, right? So gravity is and springs do the same thing. They give back whatever they originally took away regarding kinetic energy, right? So anything that does zero work necessarily around a closed path, we call a conservative force. Then, once we're talking about conservative forces, I'm at the fourth equation now, and then I'm going to move on back. I'm just, again, this is like a summary. If it makes sense, great. We can all move on. If any of it is fuzzy or doesn't make sense or went too fast, you're going to like send me a note. But equation 4, I'm saying, well, once we're talking about purely conservative forces, F sub C, once you have a force like gravity or like the spring force, or maybe both might be acting like in the lab where you have vertical springs, if the forces that are acting are purely conservative, that means we know in advance that any kinetic energy they take away from you on your way away from equilibrium, they'll give back on your way back to equilibrium. Like we know in advance that if you complete a full closed path, your total work done, the total work done on you will be zero, and the total energy change will be zero. So we say, from here on in, we say that there's this thing called potential energy. That should be a triple equal sign here. Sorry, in the fourth equation. That should be a triple equal sign. Potential energy is the work. Like, remember, what's the point of work? It gives you energy. When you do positive work on something, you give it kinetic energy, right? Well, from now on, we're going to say there's this thing called potential energy as well. And potential energy is associated only with conservative forces. There's no such thing as the potential energy due to friction. There's no such thing as the potential energy due to like tension or something. But there is a such thing as the potential energy due to gravity or due to springs or due to the electrostatic force. Because what potential energy is just a prediction of what you're going to get back on your way back from some displacement away from equilibrium. So look at the integral. We're saying potential energy is the work that would be done on you by the conservative force to bring you back from some spot, call it x naught, to the equilibrium position, call it 0. In other words, all conservative forces, these ones that are always bringing you, that always give these forces that do a total amount of 0 work for any closed path, they always have some kind of equilibrium association associated with them. What did I just say? Some kind of equilibrium position. So, like springs have that center point that where the spring is relaxed. Gravity has the floor or the ground. When anything moves away from equilibrium, we can consider that one-way trip the first half of a round trip, right? We could say if you're flying away, if you're being thrown up away from the ground on your way up, gravity is up to a height h from the ground. Gravity is doing negative mgh work on you. It will take away negative mgh worth of kinetic energy. But when you get to that height h, we know in advance if you fall back down, when you fall back down, gravity is going to do the exact same amount of work on you to return you. It's going to do positive mgh on you. So we don't have to do the calculation all over again. When something is at height h, we can just say, oh, we could look at the integral once and for all and say, oh, the amount of work that the conservative force of gravity will do on this m to bring it back down a height h to the ground, it will do mgh on it. So and therefore give it that much worth of 1f mv squared. So from now on, the amount of work that a conservative force would do to bring something from equilibrium to, from an arbitrary spot to equilibrium, that amount of work of bringing back the kinetic energy when it falls back to equilibrium, we can say is stored as potential energy. Where is it stored? In our mind. It's really just a prediction of what will happen that we know in advance and saves ourselves computational time because we know in advance that a conservative force necessarily does 0 work around any closed path. So because of the definition given in equation 3, we can establish the definition in equation 4, potential energy, and that's just true from all time. And that's where we get energy, the idea that if all the forces doing work on you are all conservative, then at any two spots, all you have is some big, like whatever you're missing in kinetic energy, we're saying you're storing as potential energy. We're just saying we know that eventually when you get back, you'll get it all back as kinetic energy. So the sum of your kinetic and potential at any one spot is the same as at any other spot. Okay, that's now that's a lot. I know there's only 12 minutes left of class. I know. But that's the background for everything we did in question 4 and 5. I do want you to know it. I want you to understand that a conservative force is a force that does no work around a closed path, and therefore conservative forces allow us to define things called potential energy functions, which are the works that the conservative force would do to bring us back to equilibrium. That's what those equations, those 4 equations, not the circled, but those 4 equations on the board, that's what they're meant to capture. Hopefully you took some kind of notes on that, or this. Again, if you have any questions about that, we're responsible for that material. So that's my summary of it. If you have any questions, please email me. I know I have 12 minutes now. What I want to do now is I want to go. So in my mind, we just did we did everything. We said everything there is to say about question 4 and 5 and 6 and 7. 8, there's still some things that we could say, but I'm going to skip that for now because we're running out. I want to go straight to question 9. And we're just going to, I know we're not going to finish it today. That's fine. So question 9, the hardest one. Okay. Here's the situation. So that's step one, right? And there are numbers given, but I don't even care about the numbers. The question is at t equals 1, what is x, right? That's what the question is asking. So, okay, yeah, we're at question 9, homework 1A. At t equals 1, what is x? Okay, this is a very simple question. That doesn't mean it's an easy question. We need to get, we want. Now, we ultimately, it wants a number, but the number is not the hard part. What we're looking for here, we want x as some kind of function of t, right? That's what we're looking for. If I could get some kind of rule where you spit in t as the input and it spits out x as the output, then I'd be ready to just plug in. That's what I want, is some kind of x as a function of t. Now, as the homework indicated, x equals 1f at squared plus v naught t is an example of x as a function of t, but it's not the right, it won't work here because we've already established a is not constant. So we need a new, so any of our old functions from physics 203 won't work. And that's why we were doing all this stuff with energy and work, because what's happening now is f is a function of x. X is the independent variable. So we're doing all this work and energy stuff. But now finally in question 9, it's trying to bring us back to fundamental physics. It's saying, okay, you could do all this stuff. Like you could figure out the speed over here at this spot using the speed over there at that spot. But what if I just want to ask you straightforwardly, what is the position or the speed at this time? Like, what are you going to do now? And my first instinct is, I don't know. I don't know anything about time for this. I don't, right? So, that was step 1. This is step 2. So what could I possibly do for step 3? Like, what do I know? Now, many of you started writing down things in your homework like cosine functions or x equals a cosine omega t. That's all correct. Like, I'm not saying that's wrong. That's awesome. That is what I'm ultimately going to derive here. But you can't just say that. I mean, you can do whatever you want, but and if you got it from the web, that's cool. That is not cheating. Or if you got it from an old video of mine, great. That is not cheating. But you get the understanding from the old video or from the web and then explain the understanding and the reasoning. What do I know right now about the universe or about space or time or physics? That's what I first put for step 3. What I know right now, what's been established, I know that F net always equals MA. Like I know that, right? Or I don't even have to worry about vectors so much. I mean, it's true, but okay. And I know that specifically we're dealing with a spring here. So I know that the force exerted by the spring is the elastic force. It's Hooke's law, F equals negative kx. That's what I know. Now I got to do something with these things to get somewhere. To get somewhere in step 4 and start getting some new knowledge of how to analyze a spring. So there's one other thing I know from calculus. I know that acceleration in calculus is defined to be the derivative of position with respect to time, right? Like, in other words, I know acceleration is dv dt, which is to say the derivative of dx dt, right? Which is to say acceleration equals the second derivative of position with respect to time. Like that's a definition. It's like from calculus class, maybe more than it is from physics, but it's true that what we mean. And why am I even caring? Because I've got F net equals MA, but I'm looking for something that relates X to T, specifically something that's going to relate X as the dependent variable to T as the independent variable. So that's my key right there, is that A can be understood in X and T terms if I think calculus. So these are my GDPs. This is what is legitimately known already at this point in our physics journey. Excuse me. So now I can start doing step 4. And I can put these together and say, okay, for this situation, then the only force like net force equals mass times acceleration, but the only force acting here is the spring force. So that is the net force. I mean, it's the only force acting, right? So, and I can go back in a second if you want. So I can say negative kx equals ma. This is all step 4, right? Yeah, because I'm like now applying to this particular problem, the problem of a mass on a spring. And notice I'm not even thinking about numbers at all. I'm just trying to like figure out some physics. So negative kx equals ma. And we just said that a is equal to d2x dt squared. In other words, this, right? So this is true. This is true of this particular problem, but the only thing it's assuming about this is that it's what a spring is exerting on some mass. Like, so in other words, right? So now this is starting to look good, or at least helpful, because now this is a constant, right? Doesn't change for a given spring. This is a constant. Everything else in there is a variable. The two variables in there are x and t. Um, um, the way they're written, with the x on the top and the t on the bottom, it's explicit that t is the independent variable, the input of some function, and x is the dependent variable. So this is what we want. I mean, it's not the answer. We're not done. But this is the kind of information we're looking for. We're looking for we want an x of t such that, wait, sorry, go to the next page. Like if I simplify this, if I divide both sides by m, just to make this clear, if I divide both sides by m, I have this. So we want, I'll write this again. It doesn't answer our question, it sets up our question. But apparently what this is saying is we want an x as a function of t such that two derivatives of x returns x itself times a constant of some kind times -1, right? Like literally, this is saying, and I know we have 2 minutes left. This is what's called a differential equation. This isn't an answer, but it's close. It's saying, I don't know what, we're looking for x as a function of t. I don't know what it is yet, but it's going to be some x such that when you take a derivative of it and then take a derivative of it again, you get back x itself times some kind of constant times a negative sign. That's what it's saying. Now, what x would that be? Because I'm going to explain this in far more detail on next class, and this is what you practice a lot in homework too. But to cut to the chase, since we only have 1 minute, if you picture this in the lab, if you picture a mass going back and forth between positions throughout some time interval on the clock, you could picture that the lab data would be a cosine graph. And if you try some kind of cosine function, cosine is a good thing to try. This doesn't prove anything. I'm just saying, picture a cosine graph. Why? Well, first of all, because we're talking about something that's going back and forth smoothly in time, like if you picture the lab. But second of all, because the derivative of cosine is negative sine. And the derivative of negative sine is negative cosine. So cosine is definitely an example of a function for which, I know it's 1:30, just let me finish my sentence, we're done. Cosine is a example of a function which, if you take two derivatives of it, you get back itself times negative times a constant 1. So the only, right? So cosine is a good thing to try because it meets that standard of differentiate it twice, you get back itself times a negative sign. The only question is there anything, are there going to be any constants? Like what are the details of the cosine function? And yes, I'm going to guess this. And I'm going to guess for the moment this. Why? Try it. This is the whole point of homework 2. We're going to end right now. But maybe it looks like I just took that out of thin air. But if you try it, meaning if you take a derivative of that and then take another derivative of that, you'll see that you get negative k over mx. So that is what you want and then you can plug in your values to get your answer. And the answer will be 0.116 meters. So I went really fast. I will back up and explain this in more detail next class, I promise. But that's the logic of it. All right. So okay, we went over time. So you gotta, okay, I'll just stop. That's good for now. Thank you for paying so much attention. I'll hang out for a second if there's any questions, but we're done. I'm turning off the recording. See you next